Hello everyone. Okay, let's look at to the next problem. Problem 7.26, page 341. So if you can read from the questions, we are given a set of wire transmission lines whereby the first line current positions at 0, and it carries a positive current which flowing to the positive z directions, and also we have another line current positioned nearby at these positions, and it has a return current which flowing to the negative z directions. And now, since we know that in terms of practicality, normally we have the very long line transmissions compared to the radius and also to the distance of separations, so we can simply assume that this is a case of infinite line current. Therefore, we can simply use the Ampere Circuital law to find the H field that due to these both line currents. Okay, so now we know that the two line currents here will have their own H field, so we can simply add up them, whereby H at P1 positions is actually a summation of H due to the first line current plus also H field due to the second line current. Since we have assumed that this is a very infinite long line current, so we can simply use the equations of finding the H field due to line current as given here, I over 2 pi r phi, right? So that's the general equations in finding the H field due to any line current that very long in extent. So now, since we have two line currents, so we can have two terms of H equation as here, the I number 1 equal to 2 pi r1 phi number 1, and plus the second one here, again I2 over 2 pi r2 phi number 2. Alright, so guys, in this case, if we just add up as shown here, we don't really see what is the exact directions of the H field appear at this particular positions. So it's good, or it's better for us to simply convert the unit vector of phi here to the respective Cartesian components, whereby we can simply use these equations. So let's say the first one, the phi number 1, we can find the conversion of this phi 1 by performing cross product between the unit vector of line current number 1 over unit vector of radius number 1. Alright, so this is a general equation how we convert from the phi to the Cartesian components s, y, or z. So now look at from the diagram, we know that the line current number 1 here flowing in a positive z directions. So this term you can simply change to the positive z directions. Alright, and again, what is the R1 value? The R1 value, guys, actually we measure from the line current perpendicularly to the point of interest. So by right, this should be our unit vector R number 1. Alright, so we know that from that diagram, the ER1 is actually in a positive x directions, positive x directions. So if you form the cross product between these two unit vectors, you're going to have finally equal to the y component. Alright, so let's proceed to the next phi, which is phi number 2. We're going to find the output for this cross product. So let's say again the phi number 2, which is belong to this second term. Again, we can simply find the output by performing cross product between the unit vector of line current number 2 cross unit vector of second radius. Alright, so if you see from the diagram, the line current number 2 actually flowing in negative z directions. So you can simply change to this term or this unit vector becoming negative z directions. And how about the R2? The R2 is actually the unit vector that pointing normally or perpendicularly from the line current to the point of interest. So that should be our unit vector of R number 2, which is in negative x directions. So again here you can simply change to negative x directions. Then we can perform the cross product between these two unit vectors and we have output positive y. Alright, so let's substitute all the value or the unit vector for the phi 1 and phi 2 into these equations. We'll find finally at here the h at P1. So the I1 given as 5 ampere, so just put 5 and 2 pi. And how about the R1? R1 actually half of distance here, which is 0.05. And now we have phi1 equal to positive y. And plus the second one here, guys, I2 again, we just consider the magnitude because we already take into account the direction inside this conversion. So here we have taken into account the line current direction. So here we just take the magnitude of it. We just put 5, 2 pi, 0.05 meter. And again, the phi 2 is equal to the positive y directions. So if you proceed the calculation, you can find the value of these equations. We have here the total h that exists at P1 position is equal to the 31.831 y directions ampere per meter. Alright. Okay, now let's turn to the next questions. Now we are going to find the H field but in different positions at P2. Located here, mentioned equations 10 cm, 5 cm. So there's the positions of point of interest for this second case. Again, we are going to analyze both line currents to find the H field from different two line currents that actually appear at these positions. So again, we have used the same method or steps. The H at P2 is actually summations of the H between first line current plus to the H that due to the second line currents. And since we have assumed that this is a very infinitely long transmission line, so we can simply use the standard equations of line current given as here. The I1 is over 2 pi R1 phi 1 plus the I2 over 2 pi R2 and now the phi number 2. Alright, so look at carefully for the first line current here, right? Is I number 1 and this is our I number 2, which is in negative z directions, and this is positive z directions. Alright, let's look at the first one, the first phi 1 here, guys. The first phi 1 here actually can be represented using these equations, which we can perform the cross product between the unit vector of first line current with the unit vector of R1, which actually joining the line from line current to the point of interest. So in this case, this is our R1 line or R1 vector. Let's say I denote as R1 vector. Okay, So the R1 here actually, guys, the unit vector for this vector of R1 that pointing from a line current to the point of interest. So we know that the L1 here actually always in positive Z. So again, this one is same, we don't have any difference. Now we have a positive Z directions. And now how do we find the unit vector of vector R1? So same of the first lecture here, the AR1 can be obtained using the vector of R1 over its magnitude. Right. So if you see closely from the diagram, the vector of R1 can be obtained by summations of two vectors, which is from here one vector and then plus the other one over here, second vector. So in other words, we can see that the R1 vector is actually equal to the 0.1 in x component, positive x, and again plus 0.05 in y component. So now we have here 0.05 in y component, and over its magnitude I have here 0.1 square, 0.05 square, and now square with everything. So that's the expressions of the vector of R1. Alright, so now let's perform the cross product between these two unit vectors. So now we have here the positive Z and then cross with 0.1 in x component plus 0.05 y component, and over its magnitude given as 0.112. So let's perform cross product between the z and x, also the z and y. So the z cross x is going to have here a positive y, and the z cross y is going to have here a negative x. Alright, so let's proceed now. After you perform cross product, you're going to have this value is about 0.447 x component plus 0.894 y component. Alright, that's done for the first phi 1. Let's do the same method or same process to find the phi 2 conversions. So again, the phi 2 unit vector can be converted to the Cartesian components by performing this cross product between unit vector of line current number 2 cross unit vector of R number 2. Right. So again, unit vector of line current number 2 doesn't change, it always in negative z direction. So here just put a negative z directions, and the R number 2 actually, guys, actually the unit vector that pointing or parallel to the vector from line current to the point of interest. So that should be your R2 vector, right? So now to find the unit vector just over its magnitude. So we're gonna have here simply here gonna have positive y directions because along the y-axis. So now again we perform cross product between the AL2 and AR2. Now we're gonna have here the z cross y gonna have a minus x, minus times minus got a positive x, right? That should be the output of this cross product between these two unit vectors. And now let's substitute all the value into this equation here. So the h at p2 is actually, the first one here is 5, 2 pi, and put 0.112 and replace the phi 1 with these equations. negative 0.447x plus 0.894 y component, and again plus the second term over here, I2 still have to put 5. Just take the magnitude because we have just taken into account during these operations in z minus z, so just take the magnitude. So the 5 here have 2 pi and the length R2 becomes 0.05, and also the phi2 now becomes positive x. Alright, so if you proceed the calculation, you can simplify the equation. You're going to have these final equations for the total H that appear or exists at position of P2 is equal to the 12.734 x component plus 6.363 y component, and the whole term has unit of ampere per meter. Alright guys, so this is the way how we can solve the problems to find the H field that actually exists at this particular point due to the both line current. Alright, so I hope you can do it yourself and make sure you get the same answer as mine. So alright, thank you and all the best.